Chapter 11.3 Binomial Theorem. Pascal's triangle. In Pascal's triangle, each row begins and ends with 1, and then as you move down the rows, the interior numbers are the sum of the two numbers above it to its left and right. So here we have Pascal's triangle. We can see that the outside numbers of each row are always 1. Then as we move down, the interior numbers are the sums of the numbers above it to its left and right. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. And 4 plus 1 is 5. We should notice a repeating pattern. So we have 3, 3, 4, 6, 4, 5, 10, 10, 5, and so on. So we see the beginning of the row and the end of the row are the same and they're mirrored. 1 plus 5 gives us 6. 5 plus 10 gives us 15. 10 plus 10 gives us 20. 10 plus 5 gives us 15. 5 plus 1 is 6. And 1 plus 6 is 7. 6 plus 15 is 21. 15 and 20 is 35. 20 and 15 is 35. 15 and 6 is 21. 6 and 1 is 7. And we could keep going, creating more rows of Pascal's triangle. So we have here rows numbers 1, 2, 3, 4, 5, 6, 7, and 8. And if we keep going, we would call that the nth row. Then the sum of each row, the sum of the first row, there's only one digit, it's 1. So the sum of that row would be 1. The sum of the second row, 1 plus 1 is 2. Sum of the third row, 1 plus 2 plus 1 is 4. Sum of the fourth row, 1 plus 3 plus 3 plus 1, that would be 6 plus 2 is 8. Next row, 1 plus 4 plus 6 plus 4 plus 1, that's 5, and 5 is 10, plus 6 is 16. Next row, we have 1, 5, 10, 10, 5, 1. That would be 10 and 10 is 20. 5 and 5 is 10, so 20 plus 10 is 30. And then 1 for each of the outsides, so 2, 32. Do you notice the pattern? These are all powers of 2. This is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5. Next one will be 2 to the power of 6, which is 64. And next one will be 2 to the power of 7, which is 128. Notice that the exponent on the 2 is always 1 less than the row number. Row 1 is 2 to the power of 0. Row 2, 2 to the power of 1. Row 3, 2 to the power of 2, and so on. So for the nth row, the sum would be 2 to the power of n minus 1, 1 less than the row number. You can continue the pattern of Pascal's triangle to solve larger pathway problems. To simplify these problems, you can use combinatorics. So we have this problem that we saw in, I believe it was 11.1, where we added up the diagonals for each of these to get the next one, kind of like Pascal's triangle, right? We're adding the two above and diagonal of those numbers to get the next one every time. But we also looked at it in terms of factorial. So we had 1, 2, 3, 4 steps to the right, and 1, 2, 3, 4 steps down. For these questions, we can always only get closer to B, so we can only go right and down for this one. So we have a total of 8 moves. 4 of them are going to the right, and 4 down. Remember that the 4 to the right are repeats and the 4 down are repeats, so we need to divide out the repetition. So writing this with factorials, we get 8 factorial over 4 factorial times 4 factorial. We can calculate that. Eight factorial over 4 factorial times 4 factorial, which gives us 70. But we can also think of this in terms of combinations, because this is the same as 8 factorial over 4 factorial times 8 minus 4 factorial, which is 8c4, n being 8 and r being 4. If we calculate that, 8c4, and we get 70. So now we see that we have another way that we can calculate the pathways from A to B for these types of problems. For this question, we have 1, 2, 3, 4. 4 moves right, and 1, 2, 2 moves down. That gives us a total of 6 moves, with 4 going right and 2 going down. Then factorially, this would be 6 factorial divided by our repetition, 4 factorial times 2 factorial. Let's calculate that. 6 factorial over 4 factorial times 2 factorial gives us 15. This is the same as 6 factorial over 4 factorial times 6 minus 4 factorial, which is 6c4. Let's calculate that. 6c4 is 15. Or we could also write this as 6c2 and check that. 6c2 also gives us 15. Remember that we said in 11.2 that NCR is equivalent to NCN minus R. So since 4 plus 2 equals 6, which is our n value, then 6c4 equals 6c2. Determine the number of pathways from A to B if you must always be moving closer to B. So this time we have different sections of the grid. So let's look at it by each section. So for this first section here, we have 1, 2, 3, 4, 5 moves right and 1, 2, 3, 4, 5 moves down. 5 right, 5 down. That gives us a total of 10 moves. Then for the next section, we have 1, 2, 3 moves to the right, and 1, 2, 3, 4, 5 moves down. That gives us a total of 8 moves for that section. So we can write this as 10 factorial divided by 5 factorial times 5 factorial for the first section. Then we would multiply because we're doing and. So we have this many moves in the first set of blocks and this many moves in the second set. So we'd have to multiply them. That is 8 factorial over 3 factorial times 5 factorial. We can calculate that. (10 factorial over 5 factorial times 5 factorial gives us 252 times 8 factorial over 3 factorial times 5 factorial, which is 56. Then 252 times 56 is 14,112. Or we could use combinations. The first set of blocks would be 10C5 times the next set would be 8C and then either 3 or 5, whichever one, doesn't matter. Calculate that. 10C5 is 252. And then 8C3 is 56, or 8C5 is also 56. Multiply them together, it's the same thing. So again, 14,112. Same thing for the next one. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 moves to the right and 3 moves down for this first set of blocks. Which gives us a total of 14 moves. Then we've got 2 right and 3 down for the next set of blocks, which gives us a total of 5 moves. And then we have 2, 4, 6 right and 2 down for the last set of blocks, which is a total of 8 moves. So in factorial form, we can write this as 14 factorial over 11 factorial times 3 factorial times the second set of blocks would be 5 factorial over 2 factorial times 3 factorial, and multiply that by the third set, which is 8 factorial over 6 factorial times 2 factorial. Calculate that. 14 factorial over 11 factorial times 3 factorial is 364 times 5 factorial over 2 factorial times 3 factorial, which is 10 times 8 factorial over 6 factorial times 2 factorial, which is 28. Multiply those together, 364 times 10 times 28 is 101,920. And then using combinations, we can write this as 14C11 or 14C3 times 5C2 or 5C3 times 8C6 or 8C2. Calculate that. 14C11 is 364 times 5C2 is 10 times 8C6 is 28. So same as above, which would give us 101,920. Pascal's triangle and the binomial theorem. The binomial theorem talks about what happens when we expand a binomial with different exponents. So our binomial here is x plus y. If we put that to the power of 0, anything to the power of 0 would give us 1. So any binomial to the power of 0 is 1. Then x plus y to the power of 1 gives us 1x plus 1y. X plus y to the power of 2, x times x is x squared, that's 1x squared. X times y and y times x gives us 2xy, and then y times y is 1y squared. X plus y to the power of 3, we get 1x cubed, 3x squared y, 3xy squared, and 1y cubed. So we can see that the coefficients of each term give us Pascal's triangle. We have 1, then 1, 1, then we've got 1, and 1 plus 1 is 2, and then we've got another 1, 1 on the outside, 1 plus 2 gives us 3, 2 plus 1 gives us 3, and then 1 on the outside. And so on, continuing on and on. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then 1 on the outside, and so on. So the coefficients in the rows of Pascal's triangle correspond to the binomial expansion, starting with an exponent of 0. So row 1 is a binomial to the power of 0, which gives us a single value, which is 1. Row 2 of Pascal's triangle gives us the coefficients for a binomial to the power of 1. We get 1x plus 1y. Row 3 corresponds to the coefficients for a binomial expansion with an exponent of 2, which gives us 1x squared plus 2xy plus 1y squared for the binomial x plus y, and so on. Notice that the row number and the exponent are not the same. The exponent is always 1 less than the row number. Also notice that the number of terms of the binomial expansion is the same as the row number. So when we expand x plus y to the power of 0, we get a single term. That's for row 1. In row 2, when we do x plus y to the power of 1, we get 2 terms. In row 3, when we do x plus y to the power of 2, we get 3 terms. And so on. In the 4th row, the expansion has 4 terms. In the 5th row, the expansion has 5 terms. The coefficients in a binomial expression can also be determined using combinations. So we have Pascal's triangle, a few rows of Pascal's triangle, and we see how they relate to combinations. So a value of 1 in Pascal's triangle is 0, C0. Then for the next row, in row 2, we have values of 1 and 1. Those correspond to 1C0 and 1C1. Then in row 3, we have 3 terms. They're 1, 2, and 1, which correspond to 2C0, 2C1, and 2C2. In row 4, we have 4 terms, 1, 3, 3, 1. And those correspond to the combinations 3C0, 3C1, 3C2, and 3C3. In row 5, we have 1, 4, 6, 4, 1, which correspond to 4C0, 4C1, 4C2, 4C3, and 4C4, and so on. An example here for the binomial a plus b, if we cube it, that means a plus b times a plus b times a plus b. We get a cubed, or 1a cubed, plus 3a squared b, plus 3ab squared, plus 1b to the power of 3. So we see that that would correspond to row 4 of Pascal's triangle for the coefficients 1, 3, 3, 1, 1, 3, 3, 1. So we could write those coefficients as 3C0, 3C1, 3C2, and 3C3. The coefficients of your answer will correspond to a row of numbers in Pascal's triangle. The row number is equal to the number of terms in the answer, which is 1 more than the exponent. So in a expansion of a plus b to the power of 3, our exponent is 3, we get 4 terms out of the expansion. The number of terms and the row number are the same, but they are 1 greater than the exponent. To find the coefficient of each term, write out your combination starting with the exponent number and choose 0 for the first term, choose 1 for the second term, etc. For the variable a, the degree descends from the exponent down to 0. For the variable b, the degree ascends from 0 to the exponent number. Notice the exponents in each term add up to the exponent on the binomial, and the number of terms in the expansion is 1 more than the exponent. So for a plus b to the power of 3, the coefficients are 3C0, so we start with the exponent number, that's our n for the combination, 3C0, then 3C1, 3C2, and 3C3. So you start with an R value of 0, you go up by 1 until you get to an R value that's equivalent to the n value. Then the first term in the binomial will start with an exponent equal to the exponent on the binomial, so a to the 3. Then that exponent will decrease, a to the 2, a to the 1, and finally a to the 0. And the second term in the binomial will go opposite. It will start with an exponent of 0 in the first term, b to the 0, then increase by 1, b to the 1, b to the 2, and b to the 3. So it will go up until it reaches the exponent value. And the sum of the exponents is going to be the exponent on the binomial. 3 plus 0 is 3, 2 plus 1 is 3, 1 plus 2 is 3, 0 plus 3 is 3. The general term is the k plus 1th term. Tk plus 1, or term k plus 1, equals nck to times x to the power of n minus k times y to the power of k. This would be for the binomial x plus y to the power of n. Example, what are the coefficients in the expansion of c plus d to the power of 5? We have that the exponent is 5, which means that n equals 5. So our coefficients are 5c0, 5c1, 5c2, 5c3, 5c4, and 5c5. Notice I'm not actually expanding this binomial c plus d to the power of 5. I'm just looking for the coefficients as it says. So I can use my calculator to figure out what these values are. I know it's going to correspond to the 6th row in Pascal's triangle. So the first and last should both be 1. Let's make sure it is. 5c0 is 1. 5c1 is 5. 5c2 is 10. 5c3 is also 10. And then we should have 5 and 1. 5c4 is 5. And 5c5. There's only one way to choose all 5 items out of 5, so there is 1. So those are our coefficients for this binomial expansion. How many terms are in the expansion of c plus d to the power of 5? Our exponent is 5. There's always one more term than the exponent number, so 5 plus 1 equals 6 terms. And we saw that above because we had 6 coefficients. Determine the simplified expression for the 4th term in the expansion of c plus d to the power of 5 if the terms are written in descending powers of c. So this is the general term formula, tk plus 1 equals nck x to the power of n minus k, y to the power of k. In this case, n is 5. K plus 1 is 4 because we're talking about the 4th term in the expression, which means that k equals 3. Take away 1 from both sides, we get k equals 3. X in this binomial, the first term in the binomial is c, and y is d. So plug in our values. T4, term 4, equals 5c3, c to the power of n minus k, n is 5 minus k, which is 3, and then d to the power of k, which is 3. Simplify this. Term 4 equals 5c3 was here, it equaled 10. 10 c to the power of 5 minus 3, which is 2, and d to the power of 3. So that is the simplified version of the 4th term in the expansion. Expand the following. 3x plus 2 to the power of 4. On our formula sheet, the binomial expansion is written x plus y to the power of n. So let's figure out what n, x, and y are for this binomial. N is the exponent, which is 4. X is the first term in the binomial, which in this case is 3x. and y is the second term in the binomial, which in this case is 2. Then to expand the binomial, starting with the coefficient of the first term, we start with the exponent on the binomial, and then C0. So it's the combination 4C0. Then we take the first term in the binomial, 3x, put it to the power of the exponent, which is 4, and then the second term of the binomial to the power of 0. For the next term, we do 4c1, so we're increasing the r value by 1. Then 3x to the power of 3, we're decreasing that exponent by 1. And 2 to the power of 1, we're increasing that exponent by 1. Continue that pattern for the next term. 4c2, we increase the r value by 1. 3x to the power of 2, decreasing that exponent by 1, and 2 to the power of 2, increasing that exponent by 1. Next term, 4c3, increasing r by 1 again. 3x to the power of 1, decreasing that exponent by 1, and then 2 to the power of 3, increasing that exponent by 1. Last term is 4c4, 3x to the power of 0, 2 to the power of 4. So our coefficients go 4c0, 4c1, 4c2, 4c3, 4c4. The exponent on 3x goes 4, 3, 2, 1, then 0. The exponent on 2 goes 0, 1, 2, 3, and then 4. Next, we want to calculate and simplify. 4c0 is 1, so we don't need to write anything for that. 3x to the power of 4, we want to bring that exponent into the brackets. So we get 3 to the power of 4, x to the power of 4. 2 to the power of 0, anything to the power of 0 is 1, so we don't need to write that. Plus 4c1, that would be 4. There's 4 ways to choose 1 from a group of 4, but we can calculate that if we need to. 4c1 is 4. Then we have 3x to the power of 3, so bring that 3 into the brackets, which gives us 3 to the power of 3, x to the power of 3, and then we have 2 to the power of 1, which is 2. Next term, 4c2 gives us 6. Then 3x squared, bring that 2 into the brackets, gives us 3 squared times x squared, and then we have 2 squared, which is 4. Then 4c3, which is the same as 4c1, is also 4. We have 3x to the power of 1, bring that 1 in, we get 3 times x, and then 2 to the power of 3 is 8. And last term, 4c4, there's only one way to choose 4 from a group of 4, so we don't need to write that. 3x to the power of 0 is 1, don't need to write that. We get 2 to the power of 4, which is 16. Continue to simplify. Our first term is 3 to the power of 4, which is 81. So 81x to the power of 4 is the first term. For the second term, we have 4 times 3 cubed times 2. 4 times 3 to the power of 3 times 2 is 216. And then our variable is x cubed. Plus, for the next term, we have 6 times 3 squared times 4. 6 times 3 squared times 4 is 216 again. And the variable is x squared. Plus, next term is 4 times 3 times 8. 4 times 3 times 8 gives us 96. and our variable is x, and the last term is a constant term 16. So here's our binomial expansion of 3x plus 2 to the power of 4. (2x minus 3y to the power of 4). Again, let's write our n, x, and y values. N is the exponent, which is 4. X is the first term in the binomial, which is 2x here. Y is the second term in the binomial, which is negative 3y. Since the general form of the binomial expansion is x plus y to the power of n, if we have a minus, then we put that with the term that it's in front of. So here, minus 3y becomes our y term. Since it's to the power of 4, our coefficients will be combinations with 4 as the n value. So 4c0 for the first one. Then first term is 2x to the power of n, which is 4, times negative 3y to the power of 0. Plus second term is 4c1, 2x to the power of 3, negative 3y to the power of 1. So again, increasing the r by 1, decreasing this exponent by 1, increasing this exponent by 1. Continue that pattern. Next term is 4c2, 2x to the power of 2, negative 3y to the power of 2, plus next term is 4c3, 2x to the power of 1, negative 3y to the power of 3, and last term 4c4, 2x to the power of 0, negative 3y to the power of 4. So in the end, this term and this exponent should be the same as n, and this exponent should be 0. Then calculate and simplify. 4c0 is 1. 2x to the power of 4, bring that 4 into the brackets. We get 2 to the power of 4, x to the power of 4. Negative 3y to the power of 0 is 1. Second term, 4c1, there's 4 ways to choose 1 from a group of 4. 2x to the 3, bring the 3 into the brackets. 2 to the 3, x to the 3. Then negative 3y, bring the 1 into the brackets. Negative 3y. Plus 4c2 is 6. 2x to the 2, bring the 2 into the brackets. We get 2 to the 2, x to the 2. Then negative 3y, bring the 2 into the brackets. Now with negatives, you want to keep the exponent outside the bracket. So negative 3 in brackets to the power of 2, and then y to the power of 2. Then 4c3 is the same as 4c1, which was 4. 2x to the power of 1 is 2 times x. Negative 3y to the power of 3, bring that exponent in, so negative 3 in brackets, then to the power of 3 times y to the 3. And last term, 4c4 is 1. 2x to the 0 is 1. Negative 3y to the 4 is negative 3 in brackets to the power of 4, y to the power of 4. Multiply our numbers together for each term. First term, 2 to the power of 4 is 16. Our variable is x to the power of 4. So first term is 16x to the power of 4. Next term, we have 4 times 2 to the power of 3 times negative 3. 4 times 2 to the power of 3 times negative 3 is negative 96. So minus 96. Our variables are x cubed y. Next term we have 6 times 2 squared times negative 3 squared. 6 times 2 squared times bracket negative 3 close bracket squared is 216. So plus 216, variables are x squared, y squared. Next term is 4 times 2 times negative 3 cubed. 4 times 2 times bracket negative 3 close bracket to the power of 3 is negative 216. So minus 216, variables are x, y to the power of 3. And last term is bracket negative 3 close bracket to the power of 4, which is 81. So plus 81 y to the power of 4. Looking at our variables, the exponents on the variables should add to the end value, which is 4. X to the 4 for term 1. X to the 3, y to the 1 is 4. X to the 2, y to the 2, that's 4. X to the 1, y to the 3 is 4. And y to the 4. So that's our expansion of 2x minus 3y to the power of 4. Finding a particular term in a binomial expansion. Example, find the 8th term in the expansion 3x minus 2 to the power of 11. The general term, this is on our formula sheet, is tk plus 1 equals nck times x to the power of n minus k times y to the power of k. N is the exponent on the binomial, so that's 11 here. X is the first term in the binomial, which is 3x here. Y is the second term, which is negative 2 here. And k, we can figure out k, we're doing the 8th term. So we're calculating T8, which equals TK plus 1, which means that 8 has to equal K plus 1. Subtract 1 from both sides, and we get 7 equals K. Then plug in all our information into the general term. TK plus 1, K is 7, so T7 plus 1 equals n, which is 11, ck, which is 7, x, the x term here is 3x to the power of n minus k, so 11 minus 7 times y, which is negative 2 to the power of k, which is 7. Then we have T8 equals 11, C7 is 330. 3x to the power of 11 minus 7 is 4. And then negative 2 in brackets to the power of 7 is negative 128. Bring this 4 into the brackets. We get T8 is 330. 3 to the 4, x to the 4 times negative 128. Multiply our numeric coefficients together, 330 times 3 to the 4 times negative 128. 330 times 3 to the power of 4 times negative 128 gives us T8 equals negative 3,421,440, and our variable is x to the 4. So term 8 is negative 3,421,440, x to the power of 4. Find the middle term of a squared minus 3b cubed to the power of 8. So recall that the number of terms in the expansion is one more than the exponent. So there are 9 terms, which means the middle term would be the 5th. If you're not sure, just write out 1, 2, 3, 4, 5, 6, 7, 8, 9, and then circle the middle one. There's 4 to the left, 4 to the right. So this is our middle. So we're looking for the 5th term, T5, which equals TK plus 1. That tells us that 5 equals K plus 1, then subtract 1 from both sides, and we get 4 equals K. The n value is the exponent on the binomial, so that's 8. The x is the first term in the binomial, a squared. The y is the second term, in this case it's negative 3b cubed. So T5, which we're trying to find, is n, which is 8, ck, which is 4, x, which is a squared, to the power of n minus k, so 8 minus 4, times y, which is negative 3b cubed, to the power of k, which is 4. Then simplify and calculate. T5 equals 8 C4, which is 70, times a squared to the power of 8 minus 4 is 4. Then we have negative 3b to the 3 to the power of 4. Bring that 4 in. We get negative 3 in brackets to the power of 4 times b to the 3 to the 4. That gives us T5 equals 70. A to the power of 2 times 4 is 8. Negative 3 in brackets to the power of 4 is 81. And then b to the power of 3 times 4 is 12. Multiply 70 and 81 together. 70 times 81 is 5,670. So T5 equals 5,670. A to the 8, B to the 12. Find the constant term, which means we have no variable, of 2x minus 1 over x squared to the power of 18. N is the exponent, 18. X is the first term, 2x. Y is the second term, negative 1 over x squared. And k we do not know, because we don't know which term number we're finding, so we don't know which k value we're looking for. Let's put what we do know into the formula. T k plus 1 equals n, which is 18 ck. X is 2x to the power of n, which is 18 minus k. Y is negative 1 over x squared to the power of k. Let's simplify and calculate what we can. T k plus 1 equals 18 ck. Bring this 18 minus k into the brackets. 2 to the power of 18 minus k times x to the power of 18 minus k. Bring this k into the brackets as well. We get negative 1 in brackets to the power of k divided by x to the power of 2k. Let's switch the order of this and this so that we have the x's together in a fraction. Since we're just multiplying, it doesn't actually matter what order we multiply in, so we can write this as t k plus 1 equals 18 ck, 2 to the power of 18 minus k, then negative 1 to the power of k, x to the 18 minus k over x to the 2k. Since this is a constant term, they tell us that up here we have no variable. That means that these x's are going to have to be the same exponent so that they divide to equal 1. So let's determine the value of k that makes x to the power of 18 minus k divided by x to the power of 2k equal 1. I can multiply both sides by x to the power of 2k to move that over. Then I get x to the power of 18 minus k equals x to the power of 2k. If these x's are equivalent, that means the exponents have to be equivalent. So I can drop the x's and say that 18 minus k equals 2k. Then put my k's together on one side, so add k to both sides. We get 18 equals 3k. Divide both sides by 3. And we get 6 equals k. Once we know the value of k, then we can actually determine the value of the term. So for k equals 6, we have t6 plus 1 equals 18c6 times x, which is 2x to the power of 18 minus 6, times y, which is negative 1 over x squared to the power of 6, which gives us t6 plus 1 equals 18. C6 is 18,564. 2x to the power of 12. 18 minus 6 is 12. And then negative 1 to the power of 6 over x to the power of 12. Then t6 plus 1 equals 18,564. 2 to the power of 12. X to the power of 12. Negative 1 to the power of 6 is positive 1 over x to the power of 12. Then we have x to the 12 divided by x to the 12. Those divide out. And we're left with 18,564 times 2 to the power of 12. Calculate that. 18,564 times 2 to the power of 12 is t6 plus 1, or t7, equals 76,038,144. So that is our constant term. We can tell that we did it correctly because our x values ended up canceling out, which is what makes it a constant term. We have no variables. Find the numerical coefficient of the x to the 11th term of the expansion of x squared minus 1 over x to the power of 10. So n is the exponent, which is 10. X is the first term, which is x squared. Y is the second term, which is negative 1 over x. And k, we don't know yet. So this is similar to the last question. Let's plug in what we do know. t to the k plus 1 equals n, which is 10ck, x, which is x squared to the power of 10 minus k, y, which is negative 1 over x to the power of k. Simplify this a bit. 10ck times x to the power of 20 minus 2k, since we multiply these exponents together, minus 1 to the power of k over x to the power of k, bringing this exponent in. Rearrange this so the x's are together in the fraction, like we did for the last question. 10ck, negative 1 in brackets to the power of k, x to the 20 minus 2k over x to the k. This time we don't want the x's to cancel out. We want them to become x to the power of 11. So find the value of k that makes x to the power of 20 minus 2k divided by x to the power of k equal x to the power of 11. I can multiply both sides by x to the k, or another way I can do it is use the exponent laws from Math 10c, which means we subtract the bottom exponent from the top exponent. So x to the power of 20 minus 2k minus k equals x to the power of 11. Then if those are equivalent, the exponents have to be equal, so 20 minus 2k minus k, which is minus 3k, has to equal 11. Then we can subtract 20 from both sides. We get negative 3k equals negative 9. Divide by negative 3 on both sides. And we get k equals 3. Now that we know the k value, we can go back and plug that into our term. For k equals 3, we have t3 plus 1 equals 10c3. I'm just copying down this, but changing all my k's to 3's. Bracket x to the 2, close bracket, to the power of 10 minus 3 times negative 1 over x to the power of 3. Then 10c3 is 120. X to the power of 2 to the power of 7, and negative 1 to the power of 3 over x to the power of 3, bringing that 3 inside. Then multiplying these exponents together, we get 120 x to the power of 14. Negative 1 to the power of 3 is negative 1 over x to the power of 3. Then x to the power of 14 divided by x to the power of 3 leaves us with x to the power of 11 on top and no more x on the bottom. So we get 120 times negative 1 is negative 120. X to the 11 is the T4 term. We just want the numerical coefficient of this term. The numerical coefficient of the x to the 11 term is negative 120, the number in front of the variable, negative 120. Again, we know we did this correctly and got the correct value for k, because when we plugged k equals 3 in, we got our x term to simplify down to x to the 11, which is what the question told us we should get. One term in the expansion of 2x minus m to the power of 7 is negative 15,120 x to the power of 4, y to the power of 3. Determine the value of m. So let's write down our values. N is the exponent, which is 7. X is the first term in the binomial, which is 2x. Y is what we're trying to find. At the moment, we can write it as negative m, but that is what we are trying to figure out. What is m? And k we can figure out by looking at the exponents on the variables here in this term. We have x to the 4, y to the 3. So x to the 4, y to the 3. If we add those together, 4 plus 3 equals 7, which is our exponent. So since those add together, that tells me that my k value is 3 because it's the exponent on the second variable. It also tells me that the variable portion of m is y. Or the variable portion of negative m is y. So let's plug in what we know. T 3 plus 1, since we just figured out that k is 3, equals 7c3 bracket 2x to the power of 7 minus 3 bracket negative m to the power of 3. 7c3 is 35, so 35 bracket 2x to the power of 4 negative m to the power of 3. Bring this 4 into the brackets. We get 35 times 2 to the 4 x to the 4 negative m to the 3. Multiply 35 times 2 to the 4. 35 times 2 to the power of 4 is 560. So 560 x to the 4 negative m to the 3. Now we know what this is equal to because it says right here that this is equal to negative 15,120 x to the 4 y to the 3. So we can write that here, negative 15,120 x to the 4 y to the 3. Then we can divide both sides by 560 x to the 4 to get the m term by itself. And on this side, x to the 4's divide out. Negative 15,120 divided by 560 is negative 27 y to the 3. On this side, 560 divides out with 560. X to the 4 divides out with x to the 4. And we're left with negative m to the power of 3. We want m, not m to the power of 3. So if we take the cube root of both sides, then we get cube root of negative 27 is negative 3. Cube root of y cubed is y. And the cube root of negative m cubed is negative m. So negative 3y equals negative m. We want positive m, so divide both sides by negative 1. And we get 3y equals m, or m equals 3y. And we could test that if we wanted. We could plug it back in here for m and calculate and make sure that it equals negative 15,120, x to the 4, y to the 3. That brings us to the end of chapter 11.3, the binomial theorem, and also the chapter 11 notes.